Hello and welcome back to another video. In this problem, we're told for the limit as x approaches 1 of x cubed plus x plus 1 equals 3, use a graph to find a value of delta that corresponds with epsilon is equal to 0.4. So this is referring to the precise definitional limit, which states that the limit as x approaches a of f of x equals L if for every epsilon greater than 0, there is a delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. And so if f of x, if a is 1, right, that's the value that x is approaching, we have the absolute value of x minus 1 is less than delta, and we can ignore this 0 for now. If this is true, we're basically saying that x minus 1 is less than delta and it's greater than negative delta. In solving this, we're saying that x is between 1 plus delta and 1 minus delta. So we basically have x values that are shifting away from 1 in a range, and we can go out as far away from 1 as delta. If this is true, then f of x, which is x cubed plus x plus 1, minus L, which is 3, right, the value of the limit, this is less than epsilon, right? And so what we basically have to do is we take this and we say x cubed plus x minus 2 is less than epsilon. We say, okay, we have to have a for x cubed plus x minus 2 is less than 0.4. We are basically saying that for a certain delta where x is varying from 1 by that much, the function can vary by up to 0.4 from 3, which is the value at 1 itself. So if we have our function here, right, graphed, and we look at the differences between the value of the function, right? So what is the value of the function? Actually, we don't need those quite yet. The value of the function at y equals 3, right? That's where we're looking at the limit as it approaches that value, right? And we're taking it up to 0.4 away, right? So 0.4 up and 0.4 down. So at 2.6 and 3.4, we're basically saying how far away in x can we go and still remain within that range. And so if we zoom in here, we can see that this occurs, right, at roughly 1.516. Okay, so 1.516, and our values here are 1.567 and 1.462. 1.567 and 1.462. And we are basically saying that there are corresponding values of x, corresponding values of delta, such that this is the distance, delta, between these two ranges. And so what we can find here is that if we take 1.516 minus 1.462, we get that that is equal to 0.054, and 1.567 minus 1.516, right, this is equal to 0.051. And so we take the more restrictive delta, 0.051, we say that this is what this is equal to, right? And so that is our value of delta. And we are told then to use a computer algebra system to solve this equation, x cubed plus x plus 1 is equal to 3 plus epsilon, to find the largest possible value of delta that works for any given epsilon greater than 0. So if we solve this equation, right, have it pulled up in Mathematica, we can see that we get these crazy long outputs, right? These are the solutions, which I'm not going to include here. I'm not going to write them out by hand, but we have these, right, that are caused by solving this equation up here. And we are solving it for x, right? And these are the outputs of x. And if we solve it for an epsilon of 0.4, right, that just means we have to take epsilon, which I wrote as v just because I couldn't just type in epsilon on my computer. We plug it in here, then we get these outputs. And this is imaginary, this is imaginary, and that 1.09327 this is our maximum possible delta. Right? And so we can compare that and find that it is different from the graphical analysis that we got earlier.